Right, this video is on the calculations behind wavelength, frequency, and energy. So we've spent some time discussing parts of a wave and what wavelength and frequency and energy are and kind of how they're related, and even this idea of direct and inversely proportional relationships. But what we need to focus on now is the math behind that. So quickly, to kind of go back over a couple things, wavelength is defined as the distance between the crests of a wave. And so that would be like from this crest to this crest, and whatever distance this is here would be the wavelength. Now, something we did not talk about before is the fact that wavelength and frequency are both given Greek letters to denote them. Okay, so where you might think that like wavelength would get the variable W, that's not the case. So wavelength gets a Greek letter that is known as lambda, and it looks like kind of like a diagonal line and then a little like curve. I don't know really what to call that, but that is the symbol for wavelength, and so it is the Greek letter lambda. Okay, and we're going to be using that to denote wavelength. So it's important that you know that lambda is wavelength. So, okay, now because wavelength is a distance, okay, it can be measured in any length unit. So if we were going to talk about the units for wavelength, a very common unit is the meter. Wavelengths could be in centimeters. Wavelengths could even be in millimeters. Okay. However, what we're going to come to find out is that wavelengths are normally very, very small. And so we need a unit that's even smaller than the millimeter. And so that unit that we're going to see so often is the nanometer. Okay. It gets the abbreviation NM. And for your, records, you need to know that 1 meter has 1 times 10 to the 9th nanometers. And so this is going to become a conversion factor that we're going to use. And it does not need to be memorized, of course. It's just like looking up, how many centimeters are in an inch, okay? But this is one we're going to see a lot in this section. The other variable that we spent some time discussing is frequency. Frequency is a little bit trickier to explain, and I kind of defined it as the number of wave crests that pass a point in a given amount of time. Okay, and so in our last discussion, we talked about a wave that looked like, let's say this, versus a wave that perhaps looked like this. Okay, and we compared their frequencies. However, I have forgotten to tell you that just like wavelength has lambda as its variable, frequency also has a variable, but it's the Greek letter nu, but it looks like a kind of cursive-ish V, but that is the Greek letter nu, and it represents frequency. Okay, so if we were going to compare these two waves and think about, like if this was my point in space, and we were going to think about how many of these crests past this point in, say, 20 seconds, compared to how many of these crests past this point in 20 seconds, hopefully you know that this is the higher frequency, okay, because the crests are closer together. So this would be the slower or smaller frequency. Now, what we learned previously was that frequency and wavelength have a relationship, and we're going to prove that in just a minute. So if you look at this first wave, we're going to talk about the wavelength in comparison to this wave, right? This has the larger wavelength. See, I use lambda, and then this one has the smaller wavelength. And what we have focused on in our previous discussion was this relationship right here. And that relationship is known as an inversely proportional. And what that basically means is as one variable gets bigger, the other one gets smaller. So you'll see me do this like kind of shorthand. If I have a big wavelength, then I'm going to have a smaller frequency. Okay, and I could also flip that around, vice versa. The only thing I haven't mentioned yet are what are the units for frequency. And they're a little more complicated than the units for wavelength. Remember, wavelength was a distance, so distance units solved our problem. Frequency, however, is a little bit different. It's defined as the crests that pass a point per time, okay? So, well, crests are just like a number, like maybe it's 20 of them or 50 of them or something. So the unit for frequency is kind of weird, okay? And normally it's seen as this, 1 over seconds, where seconds is normally abbreviated as S. So it's kind of strange. That's not seconds, okay? It's 1 over seconds. There's another way to write this, and you might know it from math class, which is that 1 over S is the same as S to the negative first, okay? And so you're going to see that written in several problems. There's also another common unit for frequency, and that is the hertz. That you might have heard of before. I guess the abbreviation capital H-Z. And the nice thing is that 1 hertz is actually equal to 1 second to the negative 1. I wrote that funny. Let me change that. So it's kind of like what can I compare this to? I don't know what I can compare it to. But the hertz and the second to the negative 1 are an equivalent measurement. Okay, so if you see hertz pop up, which I think it does on a worksheet or something, it's the same thing as the second to the negative first. Okay, so we've talked about units, we've talked about the definition, we've talked about inversely proportional relationship. So, oh gosh, I did not leave us a lot of room. The only other thing we have to talk about is how are these two really related? And they're related with one little formula, and it says this: C, which we don't know what that is yet, is equal to wavelength times frequency. Well, so I know this is wavelength. I know this is frequency, excuse me. And C is the speed of light. Okay, probably heard about the speed of light before. I think I referenced it in my last video. But the speed of light is a constant. It's the same number all the time. It's a very large number. And so C is 2.998 times 10 to the 8th. That's a big number. Meters per second. That's a constant. You're going to know that all the time, or we can look it up. And so what this basically tells us is if I know C, right, and I know one of these two numbers, whether it's the wavelength or the frequency, then algebraically I can always find the other one. Now, something to keep in mind, if the speed of light is in meters per second, then your wavelength, when you put it into this formula, has to be in meters, and your frequency has to be in 1 over seconds, or seconds to the negative first. Okay, so this is our formula for this part. Sorry that I shoved it in there. So now we're going to see how we can use that formula. Okay, so we'll do a couple practice. So it says if the wavelength of light is 4.36 times 10 to the negative 7 meters, determine the frequency. So let's keep track of what we have. We know wavelength. And I don't know frequency. That's what they want me to find. Okay. Well, so far, I only have one formula to work with, and that's this right here. Okay, so this is a situation where I say, yep, I got it. I'm looking for it. But then normally you would say, well, what's C? But we know what C is. We just learned it. Okay, it's a constant. So I actually have C. See, I always have C. Okay, so I have it, I don't know it. This is a very simple algebra problem, and so we're going to solve this. So you'll always see me do this, and I'm going to isolate frequency all by itself because I'm looking for frequency. So to do that, I need to get rid of the lambda. It's being multiplied, so I'll divide. So my new formula becomes frequency equals C divided by lambda. And from here, it's plugging in the numbers and working it out on the calculator. And that's it. I know C, it's the speed of light. And I know my wavelength because they told it to me in the problem. let's have a discussion about units. Okay, my meters are going to cancel. And then think about this. Okay, a lot of times students will say, oh, I'm left with seconds. Actually, we're not left with seconds, right? We're left with seconds in the bottom of this fraction, which really is 1 over seconds. And that should make sense to us because we've just learned that that is a unit for frequency. Okay, so I'm gonna dual screen this. I hope it works because I want to show you how to use your calculator in case you've forgotten. Okay, so, all right, I had to make sure it was in my recent apps. Okay, so here we go. So I am looking to do this right here. Okay, I wonder if I can zoom this. Nope, it's all right. So if you're using this calculator, you're going to enter 2.998. And then remember, you're never going to type times 10. You're going to hit the second, which is up here, second, and then the button above the 7 because it says EE. And that's what the calculator knows to be times 10. So 2.998 times 10, right, to the 8th power. And then just to make sure I don't mess this up, I'm going to put this in parentheses. So I just hit the close parentheses and it automatically put it in parentheses for me. So yeah, I'm just following my formula. So I'm going to divide that by, and then I'll go ahead and do parentheses again. So right here, 4.36. So 4.36, same thing, second, that double E button. And this time it's a -7. So -7. Close my parentheses. I'll hit enter. Now, unfortunately, this gave me a huge number. There might be a button I can push to turn it into scientific notation, but I'm not sure. It's probably in the format somewhere, and I'm not going to mess with that right now. So I'm just going to count. And let's see. I wonder if I can write on. Nope. So if I count over, I know you can't see me doing this, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Whoa! So I get something like 6 point. Now let's talk about sig figs for a second. My gosh, it's been years since we talked about that. I have 4 sig figs divided by 3 sig figs. So I'm going to keep 3. So 6.88. Right, times 10. I already forgot my number. I think it was 14. Times 10 to the 14th, seconds to the -1st is my frequency. Okay, I'm going to get rid of my calculators for a minute so that I can have my whole screen back. And let's do a second one. Calculate the frequency of light whose wavelength is 637 nanometers. Okay, so calculate the frequency. So question mark. I know my wavelength. And of course, we always know C. All right, so I start with my formula. This time I'm looking for frequency, which is the same as what I was looking for before. I want frequency by itself. I'll divide by wavelength. So frequency equals C over lambda. Plug in and go. So 2.998 times 10 to the 8th meters per second divided by 637 nanometers. Now, I did this on purpose because I want you to see this. I cannot do this. And if you look closely, you should know why. I have meters and I have nanometers. It's no good, and so I need to change one of them. This is like way back when we first learned dimensional analysis. Always going to be easier to change my nanometers, so I'm just going to jump up here. Okay, if we go back and look up what we were taught, here it is right here. Okay, that 1 meter is 1 times 10 to the 9th nanometers. Okay, so remember nanometers on the bottom, meters on the top, so I can cross out. We said 1 meter was 1 times 10 to the 9th nanometers. So I have to do that math first. So let's bring back my calculator. So let's see, 637 divided by 1 second EE to the 9th. Okay, and that time it was nice to me and gave it to me in scientific notation. I wonder why. It told me that that was equal to 6.3 times 10 to the -7 meters. Now, since I have that number in meters, I can come down here and plug it back in. Oh, I missed the 7, guys. 6.37, sorry. Let's take notice of my units. My meters cancel. Left with 1 over seconds again. Okay, let's do my math. So, parentheses, 2.998 second EE. Oh, I hit something wrong. Let's try that again. 2.998 second EE to the 8th power, close parentheses, divided by 6.37 second EE to the negative 7th. Oh, I think I can't enter that in that order. How do I delete? There it is, negative 7. Close parentheses and hit equals. Man, again, they gave it to me in a really big number. I'm going to keep 3 sig figs, 4.71 times 10. And if we count over, it's the same as the other one. It's going to be 14. And that is how I can calculate frequency from the speed of light and from wavelength. Okay. So hopefully there aren't any questions on that. We're going to do a lot of practice on this because this is something that is easily jumbled on the calculator. It's easily jumbled with the algebra, and it's easy to make some mistakes. So there's one more discussion, which is how does energy relate to all of this? And so there's a formula that says we can calculate the energy, and it's abbreviated as E, and it's the energy of a photon. Okay, well, I haven't talked about a photon yet. So a photon is just a tiny particle of light. So see, when we're calculating the energy, we're calculating the energy of one photon, one teeny tiny photon. So these values are going to be really small, and that's because in light we have so many photons, it's crazy. So when you're calculating this, it's actually the energy of one individual particle of light. So that's kind of interesting. Okay, so then from here, the formula says the energy of a photon is equal to something called H, which we don't know what that is yet, times frequency. So see, that we know. Okay, we've already said frequency is going to be measured in 1 over seconds. And H is something called Planck's constant. So again, it's a second constant in this chapter. And it is 6.626 times 10 to the negative 34. And the unit is something called a joule times a second. Okay. And I guess I should tell you that the energy in this case is measured in joules, capital J. J-O-U-L-E. It's the name of a person, and it was given that unit to measure energy. So I can find the energy of one photon, basically, if I just know frequency, right? Why? Well, because H is a constant, and I know it all the time. So frequency times H is going to give me energy. Now, there's a second variation of this formula that encompasses the addition of wavelength. So that's because if I go to, well, I'll just show you. So there's a second formula that looks like this. See, we know what H is, Planck's constant. We know what C is, speed of light. And we know what that funky symbol is, that's wavelength. And the way they got this was they took frequency and they used this formula. And they solved this formula for frequency, just like we did before, by dividing by lambda. And they got frequency equals C over lambda. So then what they did was they said, well, if C over lambda is frequency, right, then H times C over lambda is the same thing as H times frequency. Now, you don't have to know that. You don't have to ever be able to repeat that to me. But that's how they got that formula, in case you're wondering. Okay. So, where to from here? So there's two variations. Again, this is the energy of a, oops, I'm still in my eraser. Energy of a photon. Okay, so let's apply this. Let's do 2 problems and we'll be done. So, calculate the energy of a photon of light with a frequency of 5.16 times 10 to the 14th. Okay, so I know my frequency. Oh, they said S to the -1, which is 1 over S. And I'm looking for energy. Okay, so I have frequency. I'm looking for energy. We just learned the formula. Don't have to do any algebra, right? So E equals H. I'm just going to look it back up. 6.626 times 10 to the -34th joules times seconds times frequency, which they gave me. Remember, seconds to the -1 is 1 over seconds. Look what happens to your units. Boom, boom, leaving me with joules. And I just need my calculator back. All right, so here we go. 6.626 second EE, -34. This time we're multiplying times 5.16 second EE to the 14th. Oh, and they gave it to me in scientific notation. How nice. And so my answer here, let's see, to 3 sig figs, should be 3.42 times 10 to the -19 joules. Remember, I told you it was going to be a small number, right? And it's a small number because it's the energy of one photon, right? One tiny photon. All right, and number 2, calculate the energy of red light that has a wavelength of 680 nanometers. So that's a wavelength. So if we go back up in my notes, I'm probably not interested in using this formula because I don't have a frequency, but I could very well use this one. So E equals H times C over lambda. So let's see. So H, 6.626. Times, oh goodness, times 10 to the -34 joules times seconds, times C, that's the speed of light, 2.998, times 10 to the 8th meters per second, divided by lambda, which in this case is 680 nanometers. Now look at that for a second. Your joules cancel. I'm sorry, oh my gosh, your seconds cancel. And nothing else cancels because this is wrong. And I hope you know why it's wrong. Again, I have meters and I have nanometers. So that part of your brain needs to be turned on in this chapter. You're always looking for, do your units jive? So again, I need to do a quick conversion. 1 meter had 1 times 10 to the 9th nanometers. Okay, I'm gonna go ahead and do this in my head. I know what this is. It's 6.8 times 10 to the -7th meters. Right? I'm curious if you know how I can do that in my head. Well, think about this. Do you guys know this trick? 680 is 6.8 times 10 to the 2nd, right? If you're dividing by 1 times 10 to the 9th, well, you can kind of fraction this off. 6.8 divided by 1 is just 6.8. And then do you know how to do this? 10 to the 2nd divided by 10 to the 9th, you subtract the exponents. So it's 10 to the -7th. So sometimes you can save yourself some calculator work. By, oh no, okay, oh geez, by doing a little bit of mental math. So I'm going to go back up here and change the fact that now, instead I'm going to call that 6.8 times 10 to the -7th meters. Now my meters drop out. I'm left only with joules. That should make sense if it's an energy, and this is a lengthy problem, so let's do it. 6.626 second EE, -34 times, parentheses, 2.998 second EE to the 8th. I'm going to go ahead and hit enter because that's like with the numerator. And then I'm just going to, from there, divide, parentheses, 6.8 second EE to the -7th. All right, and again to 2 sig figs this time. I'm going to get 2.9 times 10 to the -19 joules. Again, it's a small number. It's the energy of 1 photon. We expect it to be a small number. So that is how to calculate energy